Now in this video we'll be talking about why we need stabilization and 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 what could be the various parameters that really persuade us to go for stabilization of transistors. Now the very first important thing is the temperature temperature dependence of collector current. Now, as we understand that the collector current consists of two parts in principle, and one of the parts is the useful part, which we call as a wanted part, and that part is beta IB, and the another part is the unwanted part, and we call that leakage current, and that leakage current is represented by ICEO. So this ICEO is what is temperature dependent. Okay, so this ICO is temperature dependent, uh, but is uh, uh, but is independent of the input current, and this ICEO, as we know, this ICEO, this is having a relation with ICBO in this format. Now, if I have to write down the collector current in principle here, then this collector current is made of two parts. One is beta IB, plus the other part is 1 plus beta ICBO. Right? Now, if we talk in general for germanium. For germanium, this ICBO, which is the leakage current, and which is dependent on temperature, that means there is variation in this current when there is variation in temperature. It has the exponential relation with it's like 0.08 times T minus T naught. So this is the correlation between the temperature and the reverse leakage current. And here we have a constant A naught, and it's the measured value of ICBO at some reference temperature T naught. So this T naught is the reference temperature, and this T is the operating temperature, right? This T is operating temperature. So moving down in this direction, we have a constant number here, and that is 0.08. And this constant number represents an average. When this T and T naught are measured in terms of degrees, in terms of degrees Celsius. So certainly something wrong is going on when there is the variation in temperature. Even though there is no problem with beta IB, but beta IB is influenced. IC is influenced by this reverse leakage current. The next important parameter that's to be considered here is what's called as thermal. This is called as thermal thermal runaway. Now, we have the collector current and the flow of collector current. What it does, it produces heat within the transistor, right? And this raises the transistor temperature, and thus the collector leakage current that we have, like ICBO, there is increase in the magnitude of this ICBO, and this certainly increases the collector current, and the increase in IC will automatically raise the temperature of the transistor, which in turn will cause ICBO to increase, right? So this process is cumulative. Basically, it goes on adding and adding, and every time the process goes on, and the collector current may become very large, and under those circumstances, there is the transistor may burn out, and this is basically the self destruction uh, of an unstabilized transistor, and this destruction can be referred as the thermal runaway for a transistor. So this is the parameter two that lays down and the importance of stabilization of the transistors. And there can be some individual variations that can be associated with these with the technology itself. I mean, in spite of tremendous advancements in semiconductor technology, two transistors, even of the same type, they do not have same parameters, right? So if they do not have same parameters, that means they cannot exactly adapt an environment what the previous one was if it is replaced by the new one. So when a transistor is replaced by another of the same type in the circuit, the variation in the parameter change the operating point. So even though the same model, the same number, the same semiconducting material, but certainly it's going to change the operating point, the Q point of the system that's out there. So this is what it meant, replacing transistor by same transistor. Does not mean that the next one that we have will behave in the similar way as the previous one was, even though they are generated at the same time, they are designed at the same time, they are grown under the similar environment. No, they will have differences in their actions. The next important thing here is stability factor. Now let's have some understanding of this stability factor. Now, it is always necessary now to keep this IC constant. As we know about the transistors, we want to have constant IC in a transistor circuit. Now, the extent to which a biasing current is successful in achieving this thing, in achieving this kind of goal, is measured by a stability factor, right? And this stability factor, if I symbolize it as S, so this gives us the measure of to what extent the biasing is going to do its job. So there are three quantities that can be the main causes of change in the collector current. And what could be these three quantities? The very first one is is ICBO, what we discussed already, this reverse leakage current. The next one can be base emitter voltage VBE, and 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 then there can be beta, the gain, the current gain, right? So if there is any variation in these parameters, they are going to have an influence on the collector current, right? So here is a need to define the factor, and that factor is called as stability factor. And we can define this stability factor as, say S, say for, in terms of collector current, say delta IC by delta ICBO at constant at constant the input voltage VB. What was it? It was in our case VB or VBB, and beta, right? So this can be one way of defining this stability factor. So we can say that this stability factor is the rate of change of collector current with respect to the collector leakage current, ICBO. And it may have different symbolic presentations in different books. So at constant what? At constant VBB, and if VBB is constant, that means the base current is constant, and beta. And similarly, we can define this stability factor as S SV. Now, how do I define it? I can say it is delta IC by delta VBE at constant ICBO and beta. Okay, so we can define SV as delta IC by delta VB, where these two parameters remain constant, but there is a change of collector current with respect to the base emitter voltage. And finally, we can have S beta, and this stability factor can be defined as delta IC by delta beta, and there will be ICBO will be constant, and VBE will be constant. So this stability factor can have these three ways by virtue of which we can define the stability. So here, what it means is, thus the stability factor is basically the rate of change of collector current, right? And where the rate of change of collector current at the given Q point, at the given operating point, relative to the parameters that we have considered in these equations, that we have calculated in these equations. So thus, if I have to calculate the total change in the collector current. So the total change in the collector current can be defined as, if I use IC as the total change in collector current. If I define as IC as total change in the collector current, so this will be S, which I measured first, S times delta IC CBO plus SV delta VBE plus S beta delta beta. Right now, for common emitter configuration, we have IC, as we have already wrote down that somewhere in the previous lecture. What is that? That IC is beta times IB plus 1 plus beta times ICBO. Now, what would I do is I would call this as, say, equation A. I will differentiate equation A. So on differentiating, I will differentiate this equation A. Now, by doing that, what am I going to get is I would like to differentiate it with respect to IC, the collected current, with respect to IC. Okay, so if I do that, what I will get here, here I will get 1, and then here I will get, I'll get beta delta IB by delta IC, right? Plus, then we have, I'm sorry, I'm taking the wrong number here. I should take this equation as equation A. So, I'm getting here 1, then beta delta IB by IC plus 1 plus beta times delta ICBO by delta IC, right? So we can have some more formulation here. That is, this one is beta delta IB by delta IC plus 1 plus beta. Then what is this? This is S. This is the S that we have considered here. This S. So S is delta IC by delta ICBO. Now we'd like to move on from here. Is that we have got this equation, and what should we do now? How to proceed from here is we would like to calculate this S here. So this S comes out to be the stability factor, where we have chosen one parameter. This stability factor comes out to be 1 plus beta divided by 1 minus beta, then delta IB by delta IC. So this equation gives me the measure of the stability of the transistor, right? So we can understand that what are the various parameters here that are dependent on the stability of that configuration, the stability of the circuit where we are making use of a transistor. It depends on beta, and it depends on the variation of base current with respect to the reverse leakage current. So same analysis can be done in terms of other parameters, in terms of other configurations. So here we understand that we try to analytically, mathematically understand the dependence of stability on some parameters of the transistor.